Looking at Newton's three laws of motion can be very interesting in general. In my opinion, looking at them being used in the real world is the best. So here are some examples of Newton's laws of motion being used. Newton's first law of motion, the law of inertia, states that an object in motion will stay in motion unless an outside force acts upon it. Similarly, an object at rest will stay at rest unless an outside force acts upon it. How come the ball didn't stay in the seat when the car stopped moving? It can all be explained with Newton's first law of motion, the law of inertia, especially the part that states that an object in motion will stay in motion until an outside force acts upon it. While the car is moving, we think that the ball is just sitting there, but in reality, the ball is in motion as well. When the car stops, the ball has a tendency to resist a change in motion, which is what inertia is. The change in motion is the car stopping, and the ball is resisting that by staying in motion as the law of inertia states. Newton's second law of motion, the law of acceleration, states that the force exerted on an object is directly proportional to the acceleration of the object. This is where the formula force equals mass times acceleration comes in. When the foursquare ball and tennis ball were rolled on the ground with the same force, the tennis ball accelerated faster. This can be explained with Newton's second law of motion. Since the tennis ball and foursquare ball were rolled with about the same force, the acceleration all depends on the mass. Since the tennis ball has a lower mass than the foursquare ball, it accelerated faster. Now how do we know that an object with a lower mass will accelerate faster? Although it was shown through a video, it should be explained mathematically as well. A way we can check this is by using the force formula F equals M A, or force equals mass times acceleration. Although we don't know the exact force that I used, all we have to do is put the same number for both equations and add two different masses. So let's just say we use the number 10 for force. So for this one, we can have the mass being 2 kilograms times acceleration. And then for the basketball, we can again put 10 for the force. But since the mass was larger, for this one we could put 5 kilograms. To find the acceleration, we just have to divide 5 and 2 from 10. So on this side, we divide 2 from 10, and then on this side, we divide 5 from 10. Once we do this, for the tennis ball, we'll have an acceleration of 5 meters per second squared. And for the basketball, we'll have an acceleration of 2 meters per second squared. So in this case, obviously, 5 is greater than 2, which means that the tennis ball accelerated faster than the basketball and had a lower mass as well. The fact that the same tennis ball with the same mass was thrown, but the second one accelerated faster, can also be explained with Newton's second law of acceleration. The only difference from the first example is that the tennis balls have the same mass, so it all depends on the force. The second ball was thrown with a larger force, so it accelerated faster. The fact that an object with a larger force will accelerate faster can also be explained mathematically with the formula force equals mass times acceleration. So on the left side, we're gonna have the first tennis ball, and on the right side, we're gonna have the second tennis ball. Since both of the tennis balls were the same one, we know that they have the same mass. So for both of them, we're going to keep the mass as 10 kilograms. And on this side as well. So we know that I threw the first tennis ball with a smaller force, so we're going to keep it on this side as 50 newtons, and we'll make it a bit bigger on the second side. So on this side, we'll go ahead and make the force 100 newtons. So now what we do here is the same as last time. We just divide 10 on both sides. And we do the same here as well. So with this, for the first tennis ball, we're going to get an acceleration of 5 meters per second squared. And for the second tennis ball, we'll get an acceleration of 10 meters per second squared. So obviously 5 is less than 10, which means the ball with the higher force had a higher acceleration, which proves that theory as well. Newton's third law of motion, the law of action and reaction, states that for every action there is an equal and opposite reaction. There are actually two places in this example that show the law of action and reaction. The first part is dribbling the ball. The law of action and reaction explains how when I bounce the ball on the ground, it comes back up to me. It's because the same force that was applied when the ball is pushed toward the ground is given back directly. This is what it means by an equal and opposite reaction. The second part is when the ball hits the backboard and comes back to go in the hoop. The force of the ball hitting the backboard is given right back to the ball, but in the opposite direction. There are probably many other examples of Newton's laws of motion going on around you when you're watching this video, so these aren't the only examples out there. I'm actually using many examples of Newton's laws of motion as I'm ending the video right now.